Hi, my name is Dan. I'm one of the instructors at Learn Kubernetes, and today I will show you how the Kubernetes instance calculator works. Let's get started. The Kubernetes instance calculator lets you estimate the correct node size for your cluster based on the workloads you wish to deploy. Let's quickly check the best instance type for a Node.js app with an estimated requests of 4 GB of memory and 1 CPU. I will enter 4 GB of memory and 1 CPU for requests, leaving untouched the settings for the cloud provider and instance families. I will order the instances from the least expensive part to the more expensive. And I will observe that the best instance is a T3A 2x large. The price per pod is $1.03. To understand how this calculator works, it's worth taking a step back and observing how resources are allocated in a Kubernetes cluster. Let's look at a node to understand how to estimate costs based on requests. Kubernetes reserves memory and CPU to run the operating system, the kubelet, and to detect when the instances run out of memory. The resources in your nodes are allocated as follows. Memory and CPU are reserved for the kubelet and the operating system. A few hundred megabytes are allocated to the eviction threshold, and the remaining are available for running pods. If you use any daemon sets or agents, you probably have fewer resources to run your workloads. But how much memory CPU is allocated exactly? Things get interesting here, since every cloud provider has a different opinion. In general, reservation for the operating system and eviction threshold are fixed, typically a few hundred megabytes each. Reservation for the kubelet are more complex, since those depend on the instance type. Here is an example of the memory reservation in GCP and Azure. AWS follows an entirely different formula. So how do you know exactly how much memory is available to pods? The calculator computes the value for you, but it doesn't stop there. It also uses the CPU and memory requests to estimate the instance that could fit as many pods as possible. To do that, it computes a resource unit based on the maximum number of pods that can run on that instance. Requests for your workloads, such as a Java app with requests of 6 GB and half a CPU, are converted to a resource unit. And finally, the allocation is estimated. This is great for assessing the maximum efficiency of your instance and the current workload. Let's explore this in practice. You can think of the calculator as having 4 distinct blocks. In the first block, you define your workload by selecting requests and limits. In the next step, you choose the cloud provider and the type of instance families you want to consider for your estimation. The calculator will use those to compute the reservations and display a list with the calculations. I find sorting the instance by pod cost helpful, starting with the least expensive. Finally, I can select the instance and explore the numbers in more detail. My focus is often on the costs, but the instance view gives me insights into other aspects, such as efficiency, overcommitment, max number of pods, and max disks. Let's start with the efficiency widget, which displays how well I'm utilizing the CPU and memory available in the instance. You might find that some instances utilize CPU or memory better. If that's the case, you might want to expand the instance families you consider in your estimation to include memory or compute optimized instances. Let's look at an example. Here I have a T3X large where the efficiency for memory is 51% and the efficiency for CPU is 26%. The application has requests of 8 GB of memory and 1 CPU. I can include memory optimized instances in my calculations, and I can see that those provide better efficiencies for my workload. Next, there is the overcommitment widget. This widget uses the app limits to visualize oversubscribed instances. Let's see why this is helpful with an example. A Go application uses 4 GB of memory and 1 CPU for requests. The limit is set to 8 GB and 2 CPUs. The best instance type for this workload is a T3A 2x large with a cost per pod of $1.03. The calculations are based on the assumption that actual memory and CPU usage is equal to the requests, but there is nothing to stop them from rising until their limit of 8 GB of memory and 2 CPUs. But what if all pods were to use all the available resources until their limits? We won't be able to host as many pods in this instance because it is oversubscribed. The overcommitment widget tracks this specific scenario as a percentage. So an overcommitment of 172% of memory means that if all pods reach their memory limit simultaneously, you will need at least 1.5 instances to host all of them. The max pod count widget displays how many pods can fit in the current instance, based on the hard limits of the kubelet, limits imposed by the cloud provider, and the requests. You might find that instances of different sizes have similar costs per pod. In this particular case, the T3A 2x large and T3A X large have got 1 cent of difference. However, one can host 15 pods, the other 32. Which one should you choose? I usually ask myself, if a node is lost, how many pods will be affected? That helps me narrow down my options. Finally, the max disks widget tracks how many disks can be attached to the current instance. This is useful if you have workloads that require persistent volumes like stateful sets. If the instance supports only 4 disks, like in this case, you won't be able to run more than 4 replicas of your stateful sets, regardless of how many pods can run on the instance. The last widget is the cost estimation widget. It displays the cost per pod for a current instance and an estimate for the error. To explain why this is useful, consider the scenario where a Python app has a request of 4 GB of memory. The assumption is that the memory usage at runtime is 4 GB. But what if the actual memory usage is 10% higher on average or 10% lower? When the usage is 10% lower, you overpay your pod by 10%. When the usage is 10% higher, the cost increases because you can deploy fewer pods in the current instance, since each pod is 10% bigger. The widget lets you play with the error rate. If your error rate exceeds 50%, the cost per pod can easily double. Unfortunately, the calculator can estimate costs and errors, but can't measure runtime performance. If you wish to have a more precise result, you should look into PurposeScale, a platform that optimizes requests, limits, and instance sizes based on runtime performance. They support the development of this tool and its new features. Once you're done exploring the current instance, the calculator lets you compare the current setup with another instance from the same or different cloud provider. Let's compare a .NET app with requests of 16 GB of memory and 4 CPUs. The best instance on AWS is an M6A 48X large. The cost per pod is $4.24. Let's compare it with an instance from Azure. If I switch to Azure, the best instance type is a D48PS V5. While the costs are similar, you can already appreciate some minor differences. The number of pods is different, as well as the max disks. You can also appreciate that with an error of 10% on your requests, the cost per pod is lower on Azure and higher on AWS. That's it for today. I hope you find this guide helpful for selecting the best instance for your Kubernetes cluster. For more educational content on Kubernetes, don't forget to follow Lake Heights. See you next time.